All right, guys, welcome back to our program here. We're moving into a new set of topics this lesson. We're going to be talking about redistribution. Relatively simple concept. I mean, redistribution is not a difficult topic to understand, but there are, some little caveats and little things that you need to consider when you're doing redistribution. And it gets a little bit more complicated when you're moving from different protocols, different types of protocols, and so on. So we'll talk about those little differences, and we'll talk about those little caveats that you have to be aware of. We're going to start by just kind of doing an overview, taking a look at, that's our lesson 54, if you will, looking at kind of redistribution from a high level. And then we're going to get into some more detailed discussion. We'll actually look at some of the configuration in this one of the lessons tonight. And I'll put this into the Google Drive for you guys. But we're going to do some mutual two-way redistribution from OSPF to EIGRP and take a look at some of the considerations that you have to take into account when you're doing that. If you're doing one-way redistribution or you're doing single-point redistribution, it's a really simple concept. Just a couple of basic rules you need to understand, but you don't really have to worry about loop avoidance and injecting routes that would cause routing problems and so on. So in this section, we're basically just going to talk about a general overview of redistribution. How does it work? We'll talk a little bit later about IPv6 redistribution because there are some minor differences between how v4 redistribution works and IPv6 redistribution works. Really just talk about the selection process and what are some of the considerations that we have to take into account when we're doing redistribution. One of the things that we need to talk about for sure is how the iOS chooses one path over another. We have some basic concepts that we understand with regard to longest match routing, administrative distance, and so on, but some of those attributes and some of those variables don't pass through the redistribution boundary naturally. So we have to consider how we're going to manage that process when we're actually doing our redistribution. Okay? And that's what we're going to be talking about. When we're looking at two different paths, and we have that maybe those paths are going to the same destination, how are we going to make a decision on what path we choose based on that information? Now, we could do this based on administrative distance. AD, of course, is going to be a huge consideration in redistribution, because in some cases, manipulating the administrative distance or leaving the administrative distance alone can hurt us, and manipulating the administrative distance could also help us as well. And we'll take a look at an example where leaving the administrative distance alone actually hurts us in our topology, and how do we fix that, right? Because we can see different symptoms in the control plane and the data plane based on different resolutions that we're doing in our routing process. All right, so obviously the whole concept of redistribution is taking routes from one routing protocol and inserting those routes into another protocol. In our topology here, we have essentially two domains that we're routing. R1, R2, and R3 are participating in EIGRP. R4 is in OSPF, and R2 and R3 are going to be our redistribution points in this topology. That's going to allow us to redistribute from one network to the other. We've got mutual two-way redistribution at 2 points in the network. So definitely a big consideration here with regard to the optimal path to choose. How do we make sure that we're doing that, and so on. All right. So yeah, we're taking routes from one protocol. We're inserting those routes into another protocol. It's a pretty basic concept. The big issue, like I said, that comes up is when we redistribute these routes, and how do we maintain end-to-end path cost and reachability information as we're going from one point to the other. We lose that visibility, we lose that functionality at the redistribution point. So when redistribution occurs, the metrics that might have been recognized by one protocol in one domain are not going to be compatible or recognized by another routing protocol in another domain. So you really have to consider how that's going to affect your path selection, how it's going to affect your route selection, and so on. All right. Also, very, very important concept here. Redistribution occurs from the routing table. It does not occur from the routing database. So if I've got routes in my routing database, that doesn't necessarily mean that those are the routes that I'm using. For example, in EIGRP, I might have successors, and then I'll also have feasible successors, and based on feasibility condition and so on, even though the feasible successors show up in the topology database in EIGRP, because they're not part of my routing information base, which are the routes that we're actually using, then I'm not going to insert those routes into the redistribution process. So it's very important that you first verify what the functionality is, or excuse me, at least what reachability is based on your routing information base first, before you decide that you're going to try to redistribute routes into from one protocol to another. Okay, so that's going to be one of the very first verification steps that we're going to run into when we're doing our process, is to verify that we have routes in our routing information base, and then we can decide how we're going to redistribute those routes into the other protocol. All right, we would obviously use show IP route in this case to determine which routes can actually be redistributed. We never, and it doesn't matter what direction you're going, it doesn't matter what IGP or EGP protocol you're using, this is always going to be the case. We'll never redistribute routes into or out of a protocol that we're not using within that protocol. Very, very important concept. So we'll take the routes that are installed in our routing information base and for that particular protocol. So let's say that we're redistributing from EIGRP into OSPF, or redistributing from BGP into EIGRP, or whatever it might be. I'll take the routes that I learned, right? All my D routes and all my DEX routes potentially, if I'm going to redistribute some of the DEX routes. But keep in mind, we'll also be redistributing the connected interfaces that are running the protocol itself. All right, in IPv4, this happens by default. In IPv6, it's slightly different because in IPv6, connected interfaces, even if they are running the protocol, are not going to get redistributed by default. That's a condition that we can override if necessary. All right, so before doing any redistribution, we want to make sure we do a show IP route. Let's say we're redistributing from EIGRP into OSPF. We'll do a show IP route EIGRP. We'll do a show IP EIGRP interfaces to make sure that we understand exactly what types of routes are going to be redistributed. In order for us to understand how the routes make it into the table, we need to understand how the routes make it into the table for different routing protocols. What I mean to say is, in order for us to understand how the routes, what routes are going to be redistributed based on the fact that they are part of the routing information base, we need to make sure how different routes make it into the routing table itself. Now, this is a basic concept, something that you guys are probably pretty familiar with regard to longest match routing, administrative distance comparisons for prefixes that are identical from two different protocols, and so on. But there are a couple of things I think you'll learn in this discussion that will apply to what we're going to be doing in this topology in a little bit. All right, so we'll talk about this from the perspective of RIP, EIGRP, OSPF, and BGP. ISIS is probably going to operate very similarly to OSPF, being that it's a link state routing protocol. So it's not necessarily something that we're going to spend a lot of time talking about, but we certainly will talk about the other routing protocols and how they will be affected. All right. In general, we really have two different types of protocols: distance vector and not distance vector. I know that we tend to classify BGP as a path vector protocol, but it does, from an autonomous system perspective, operate much like a distance vector protocol. So we have those distance vector and we have the non-distance vector protocols. If I have a route, as an example, in EIGRP, and let's say I've calculated the feasible distance for my successor, we know that that route is going to end up going into my routing information base. All right. Now, the way EIGRP behaves is if I learn another route for that same prefix, exactly the same prefix, and I've learned that other route with a lower administrative distance than EIGRP, EIGRP's default behavior is to create an infinite metric for that particular route in the topology table. So even though it's still a valid route within EIGRP, because of the behavior of EIGRP, not only do we not install the route in our routing table locally, but we also identify that particular EIGRP path with an infinite metric, which means that even if I'm doing redistribution from EIGRP into another process, then I won't be able to redistribute that particular route into the OSPF domain. So I might have to do like a redistribute static or redistribute connected if there's another route with a similar prefix or the same prefix for that particular path. All right. In the case of OSPF or in the case of BGP, it works differently because there's actually a separation from the routing database and the forwarding database. All right. So we'll talk about that in a little bit more detail later on as we get into some of the other topics a little bit later on. But in the case of OSPF and BGP, because we have that separation, there can be some redistribution, even though it may not be in the database as expected. So in the case of OSPF, within an area, we can advertise a route that we're not actually using, meaning that it couldn't be redistributed, but it might show up in the database. All right, I'll see if I can demonstrate that concept to you guys a little bit later on. The same case with BGP, right? BGP will insert a route into the database, but it will mark that route with a rib failure. So we are able to install the route into BGP, but we don't actually use it because it could cause a loop. And we can see that if we do a show IP BGP, we can identify which routes have a rib failure. They won't show up in the routing table with a BGP route, but they will show up in the BGP database. Okay, it doesn't matter in any case, right? Because as long as the route is not in the routing information base, which is our routing table, it's not going to get redistributed regardless. Okay, now we'll see more about this as we get into the details. We're going to take a look at some interesting cases where you might create a loop, where OSPF, for example, which you think is a pretty robust and intelligent routing protocol, would create a loop, but EIGRP wouldn't. Or maybe there's another scenario where RIP might create a loop, but BGP wouldn't, and so on. So just like when we were talking about DMVPN and all these other technologies, it's not so much understanding the fundamental concepts, but there's little individual cases of understanding, if you will, that you have to have in order to understand the effect that you're going to see on these different processes. Okay. All right. Based on the fact that different routing protocols have different advertising rules, that's where the knowledge is going to have to come into play. And hopefully throughout the next few lessons, with your knowledge, you should actually be able to easily predict any kind of negative conditions or detrimental conditions before you actually do the redistribution, simply because you understand what decision factors are going to come into play when we're making decisions on redistribution and routing. Okay? You really need to be able to identify or at least predict issues before you see them in the control plane in the implementation. Now, certainly you may run into a scenario where it's something you're possibly not aware of. So we're also going to talk about how to identify some of those issues. And we're actually going to take a look in this topology. We're going to create an issue with basic redistribution. All right. And we're going to see what the effect of just doing basic redistribution is in this particular case. All right. Lost my train of thought there. One of the other considerations, yeah, that's what I wanted to talk about. One of the other considerations that we have to take into account is what we do with connected routes as well. Okay. Now, when I do redistribute EIGRP into OSPF, let's say, for example, this loopback interface that we see in our topology here, because it is part of EIGRP natively on router 2, that loopback interface, if I did redistribute EIGRP into OSPF, that loopback interface would automatically be included in that redistribution process in IPv4. In IPv6, that actually would not be the case. All right. You have the option to make connected routes, to redistribute connected routes in IPv6, but by default, the behavior is to not redistribute those connected routes. Well, we're going to go through a few examples towards the end of this section, which is probably going to be in the next couple lessons, where I can show you that process and show you how we make that happen, because that may be something that you're going to be responsible for on the CCIE lab exam as well. All right. You can also explicitly include or exclude particular interfaces. We would do this by applying some sort of route map filter to the redistribution process. So I might say, for example, redistribute connected, put in my seed metric or whatever metric I might have, and then apply a route map to the redistribution process. This will override whatever implicit behavior we might have in the redistribution process. All right. Some people will ask, well, why would I not want to include connected routes as part of the redistribution process? Well, there are scenarios where you may want to exclude those connected routes because they might just be providing some sort of transit path through the network. So you're using those particular connected interfaces to route to a particular destination or through that transit link, but you're not trying to route directly to the transit link. All right, this is especially going to be the case when you have different tunneling techniques that you implement, like MPLS tunneling techniques and so on. We want to get to the traffic edge in the case of an MPLS tunnel, but we don't necessarily care about the core of the network. So in our redistribution process, we may want to filter out those transit links from the redistribution process. All right, like I said, that filtering does not happen automatically in IPv4. And there actually could be some cases where you break the network if you're redistributing the protocol and redistributing connected routes or connected interfaces, or doing both, right, in both directions. All right, so before we get into some of the configuration and verification, I just want to kind of run through a quick discussion about how Cisco IOS chooses the path. Like I said, this is something that you guys are probably pretty familiar with, but hopefully I can introduce a couple of new concepts for you. All right. Within the protocol, obviously there's going to be a decision process itself. So if I'm deciding on a path in EIGRP with dual or in OSPF with Dijkstra's SPF algorithm, we know that the path selection process, for example, EIGRP, is going to be based on feasible distance, and the path with the lowest overall feasible distance is going to be the successor path, right? And then, of course, I would go back and look at advertised distance to be able to figure out, or reported distance to be able to figure out my feasible successors. In Dijkstra's algorithm, it's overall path cost, SPF calculation, and the SPF algorithm works in that case. So choosing paths within the protocol is relatively simple. There are some considerations, of course, with regard to load balancing. ECMP would be implemented if we have destination prefixes that are reachable from equal cost paths in all protocols. But in the case of EIGRP, I might even have, with a variance option, I might even have some unequal cost load balancing options available to me. All right. Now, the load balancing is always going to be possible. It just depends on the maximum paths. It'll depend on whether or not we have multiple equal longest matches within the protocol itself. Now, if we have equal longest matches between different protocols, then we have to rely on administrative distance for the redistribution process. Again, this is a CCNA level discussion, right? Administrative distance is something that you've learned about from the very first time that you dealt with routing protocols. But we're going to talk more, and as we get into some of the other lessons, we'll talk more in detail about how we manipulate administrative distance to affect the redistribution process. All right. In fact, in this particular example, when we're doing this two-way mutual redistribution between OSPF and EIGRP, we're going to have to manipulate that value to choose the optimal path to reach a particular destination. All right. Let's say we have two /24s with the same prefix, one in one protocol and one in the other protocol. We know in that particular case, that's where AD is going to come into play. They have to be the exact same prefix with the exact same prefix length, which is going to allow us to identify whether or not it is a matching prefix. A 10.10.10.0/24 is not going to be the same as a 10.10.10.0/25, right? So if I'm getting a /25 from OSPF as an example, and I'm getting a /24 from EIGRP, both of the routes would be installed in the routing information base, but when I finally make my routing decision, administrative distance doesn't come into play in that case, and I'm simply going to use the /25 prefix to match, right? Unless it's a specific packet that doesn't fall within that range. So for like a 10.10.10.0/25, 10.10.10.129 or 150 would have to match the /24 prefix. But if we were routing to 10.10.10.10, that would match both the 25 and the 24 prefix. Okay? We actually can manipulate these values. We can hide the topology with shorter matches, or we can leak out longer matches through redistribution if we want to do some sort of traffic engineering concept as well. I'll probably demonstrate some of those concepts later on when we get into some more of the advanced examples of redistribution that we'll talk about towards the end of this section. All right, not tonight's lesson, but the end of the overall redistribution section. The end result, though, is that the route gets installed in the routing information base, and then ultimately it's going to get installed in the forwarding information base with Ceph, and we'll be able to route to that destination prefix. If I have the same protocol and equal longest matches, but I have multiple processes, right? Say I'm running two EIGRP processes, and I'm learning about the same prefix in both processes or autonomous systems, and we have equal matches. How do we decide? What if I'm running two OSPF process IDs on the same platform, and I happen to be learning about the same route prefix through both of those process IDs? How do I decide in that case what I do with regard to that routing decision, right? Well, there's another deciding factor in this particular case, and that is that in EIGRP, we would actually choose the prefix that matches the lowest autonomous system number. In OSPF, we would choose the prefix that matches the lowest process ID. All right, Mike had a question here. Let's see what that question is. That /25 and /24 example. The /25 is the longer match. Is it the same as a more specific path? Yeah, I think you could use that term, Mike. I think you could say yes. I wouldn't necessarily use the term more specific path. It is a more specific route, right? Because we always match routing based on the longest, the most number of ones in the mask that are going to match the packet that we're trying to route to, right? So exactly, it's a more specific route, which ultimately goes to a different path, possibly, or a different direction. So yes, when we say longest match rule, we're talking about a longer prefix length. But like I said, it has to match the packet, of course. A 10.10.10.0/25 prefix is not going to match a 10.10.10.150 packet, right? Because it would only go from 0 to 127 in that particular case. But yes, always longest one wins, right? If there's a tie. The only time administrative distance ever comes into play is if the prefixes are exactly the same. And we're learning about the two prefixes from different routing processes. All right. Now, again, like I said, within the same routing process, like the AD for EIGRP is 90, but I might have EIGRP Autonomous System 10, and I might have EIGRP Autonomous System 11, and both of them have a DEX route, which has an AD of 170 to a prefix that's exactly the same. Then I have to decide what route goes into the routing information base. Is it going to be the one that came in Autonomous System 10, or is it going to be the one that came in Autonomous System 11? In the case of EIGRP, we always choose the lowest AS number, so the route that was learned in Autonomous System 10 would go into the routing table. And they may actually point to different destinations, because the redistribution points into those ASs might come from a different location. All right. Now, in the case of OSPF, it's the lowest process ID. So we could be running two different processes on the same router. We would always choose the prefix that was learned through the lowest process ID. Okay. Remember, metric is only chosen after all the other tiebreakers have been selected, right? So even before we actually look at metric, we're going to look at the origin of the route itself, all right? So it is very important that you guys understand AD values for different protocols. Thankfully, it's pretty easy to find because you can simply do a show IP route and look at the code table or the code index in the beginning of that output, and that will tell you what AD values exist. But 0 is going to be connected, for example. 1 is static. 5 is EIGRP summary, but only on the originating router of the summary. EIGRP summaries are going to get converted to 90 afterwards, typically. External BGP is going to have an administrative distance of 20 by default. Internal EIGRP is 90, for example. OSPF is 110. ISIS is 115. RIP is 120. External EIGRP 170, and so on. Those are the ones that we see all the time. I don't think you guys will have any problems remembering that. That's a pretty standard networking 101 or routing 101 concept, right? On-demand routing, might see that maybe. That's 160. Internal BGP is 200. We talked about DMVPN in the last few lessons. NHRP routes go in as 250, administrative distance of 250, and infinite, meaning it's basically unusable routes, will go in with an administrative distance of 255. All right. There is a reason why Cisco chooses to order these administrative distance values in this particular order. We'll talk a little bit more about that. Mostly it has to do with, what do I trust more? Do I trust internal sources over external sources, and so on? But we can always manipulate these values. For example, you can do a floating static route that might have an administrative distance of 95 if I want that floating static route to be used as a backup, for example, an EIGRP prefix or something like that. So changing the administrative distance is one of the tools or the mechanisms that we have to solve data plane loops or to fix, potentially redistribution problems. All right. Why do we have these values, right? Why is eBGP always preferred over IGP protocols, right? While eBGP has an administrative distance of 20, EIGRP 90. So why would we do that, right? Why are IGP routing protocols going to be preferred over IBGP, right? OSPF 110 versus IBGP of 200. All right. Well, it makes sense, right? If we're if we're an edge router and we're learning a route from an external BGP source, and we're also learning a route through IGP, most likely it's going to be through some sort of redistribution process, we're probably going to know that that route doesn't really exist in our domain. It's not always guaranteed, but for the most case, that's going to be some sort of route that somebody else is routing on the internet, or from a logical point of view, from somewhere outside of your network instead of inside the network. So I would prefer the eBGP routes over IGP routes, because most likely those routes are external to our domain anyway. All right. The same could be said for IBGP versus IGP. Remember, IBGP is or actually both IBGP and eBGP are logical constructs. We could be doing multi-hop peering where we're establishing a TCP connection between the routers to exchange routing information. In that particular case, BGP doesn't really know about the topology and it doesn't have as much awareness of the domain. So we would want to go ahead and choose an IGP route, OSPF, EIGRP, RIP, and so on, over even an iBGP route. Okay. Now we can modify distance values. We can do this on a neighbor basis, or we can do it on a per prefix basis. Excuse me. We'll take a look at this from a protocol perspective a little bit later on in this particular example. All right. So why would I choose EIGRP over OSPF? Well, in the case of EIGRP actually, we've seen this a couple of different cases where EIGRP tends to be kind of more preferred, is EIGRP has a way of differentiating between external versus internal routes, right? For example, what is the administrative distance of an OSPF internal route versus an OSPF external route? Well, guess what? They're the same, right? 110. OSPF by default does not distinguish between internal versus external. And that's, by design. I mean, OSPF is a much more intelligent protocol when it comes to understanding the overall topology, but that's something to consider, okay? If both routes are actually internal to the domain, then deciding between OSPF and EIGRP is going to be a completely arbitrary decision, right? Because OSPF doesn't separate internal versus external from an AD perspective. EIGRP does, so we'd be able to identify within EIGRP whether or not the route is originated inside my domain or is coming in through some sort of redistribution process. All right. We will look at some examples where we can create a loop in the control plane. And if a loop is created in the control plane, the route might flap back and forth between two different routers. Or we could create a loop in the data plane where the packet gets stuck in a loop until its time to live expires or whatnot as it's progressing or moving through the network. Okay. So we would choose external EIGRP last before any other IGP because being that it has an administrative distance of 170, which is going to be higher than even RIP, because most likely that route is probably not within our domain. All right. Internal protocols, regardless of whatever protocol it is, usually are considered to have kind of a better understanding of what is happening in the network versus external protocols. So that's something to definitely consider. All right. When you move routes from one protocol to another, and the protocols are not compatible, right? Which is in most cases, the only time protocols are going to be compatible is if we're redistributing from one EIGRP process to another EIGRP process and so on. But in most cases, we're actually going from, say, a dual domain to an SPF domain. We're not going to be able to maintain a lot of the information that's necessary for us to make the best decisions. And that's the consideration that we have to take into account. All right, dual cannot tell the SPF algorithm to guarantee that the route is loop free, and SPF can't tell dual, let's go ahead and guarantee that the route is loop free. All right, so that's just a really basic introduction to the concept of redistribution, some of the concepts that we're going to take a look at. Obviously with redistribution, or just like any other topic we have, it's better to kind of just take a look at the configurations and kind of talk about some of these scenarios. And that's really what we're going to end up doing for the rest of the lessons in this section here, is really kind of building out different types of scenarios and taking a look at the considerations that we have in those different scenarios. All right, so now let's take a look at a basic example of redistribution. We're going to use this topology as an example. Just a basic EIGRP to OSPF. That's going to be your most common example that you're going to see anyway in most cases. Or, some sort of IGP to BGP, but when we're doing some sort of tunneling protocol. But in the case of inter-domain or intra-domain routing, it's mostly going to be, OSPF to EIGRP. All right. In other lessons, we'll actually take a look at problem cases in redistribution. We'll create those problems, and we'll identify how we can then fix those problems. All right, we're going to take a look at IGP redistribution, and then we'll take a look at BGP examples later on as well. So even though we don't have RIP running in this domain, there are some considerations that I want to take into account when it comes to RIP. Very similar to EIGRP, being that they're both distance vector routing protocols. Now, RIP is a protocol that could be used in some cases. In DMVPN phase 1, RIP is not a bad protocol to use. Summary boundaries are arbitrary, and it's pretty much an arbitrary flat design. So it's not infeasible that you would see RIP, but it's unlikely. RIP is going to have an administrative distance of 120, and it doesn't distinguish between internal versus external. That's a bit of a problem. It's one of the most basic protocols out there, but because I can't distinguish between whether a route is originated within the RIP domain or whether the route was originated by somebody else and it was redistributed into the domain, it's generally something that we kind of stay away from. The only case where that might not be the case is if, for example, you decide to do redistribution with route tagging. And we'll show you how to do that in one of our advanced topics as well, where I can actually apply tags through a route map that's applied to the redistribution process. Route tagging is a way for us to be able to identify the origin of the routes, and then also to allows us to apply filters in two-way mutual kind of two-point redistribution processes like we see in this particular case. All right, now one major thing about RIP, and this is the same case for EIGRP, both distance vector routing protocols, there is no default seed metric coming into the protocol itself. All right, so that means if I redistribute into EIGRP or I redistribute into RIP, I need to specify a seed metric in order for that redistribution to take place. Hold on one second, gentlemen. Where I left off. Okay, so there is no default seed metric. Now, in the redistribution process, we'll actually see that in this example here. In the redistribution process, there's a couple of ways that you can seed the metric. Seeding the metric means just kind of putting in a default metric. You can do it in the redistribution command, or you can specify it as part of the routing process using a default metric command. I'll show you guys that when we do our configuration here in a few minutes. The actual seed metric is going to be very significant, especially with RIP, maybe not so much with EIGRP or OSPF, because if the value is too high, you might have some reachability problems in the domain because our maximum hop count is 15. Or if it's too low, we might introduce suboptimal routing into the domain. So that's another consideration, is as you're doing redistribution, make sure that you understand what the effect of the seed metric is. EIGRP is probably one of the best protocols because it does differentiate between internal and external. Redistributed routes are going to have an administrative distance of 170, and they also have a mechanism built into them to prevent route feedback. All right, we'll talk about that. That has to do with how EIGRP handles the router ID when we're actually advertising routes into EIGRP. All right, now, again, and this is one of the golden rules of redistribution. When you're redistributing into distance vector, there is no default seed metric, or technically there is, it's infinity. So any routes going into distance vector automatically are going to be unusable if you don't apply some sort of seed metric. All right, the only time that would not apply is if you're redistributing between two EIGRP processes directly. So if I'm redistributing from EIGRP 100 into EIGRP 200, metrics carry over because both dual processes understand the effect of metrics in general because we're coming essentially from the same process. All right, or the same type of routing process. All right, and we'll talk about, again, applying redistribution seed metrics to the redistribution process by using the redistribute command and also the default metric option. In EIGRP, we actually have another component, and if you're familiar with redistribution, this may be something that you're not aware of, but we actually use the router ID for loop prevention in the redistribution process as well. Traditionally, even prior to release 5.0, let me see what we're running in our particular case. Show EIGRP plugins. we're running 11.0, so clearly 5.0 is a long time ago. So in EIGRP 5.0, the router ID is included prior to that, included in external routes, but it's also now included in internal routes as well. If we, well, the basic idea here, right, is that if a route gets looped back to me, I redistributed the route and somehow it got redistributed back to me, I'm going to look for my own router ID to see if the router that originated this route was somehow looped back to me, and then I'm simply going to ignore it, if that's the case. All right. Now, one of the potential problems you could have, and I'm going to demonstrate this a little bit later on, is that you could have two different routers with the duplicate router IDs, and then essentially from the redistribution process, those routers are not going to be able to install those routes in the routing table. All right. So let's go ahead and take a look at our topology. Obviously, the very first thing that we need to verify is our basic configuration. We need to make sure that we understand, before we do any redistribution, we need to understand that the routers have a complete view of the network, right? So I'm going to start, let's take a look at the diagram first. R4 is running OSPF. We've got 4 different areas that router 4 is participating in. It is a backbone router because it does have a loopback interface in area 0. So we're not breaking any of the hierarchical leaf spine leaf designs that we have to have for OSPF. 1.100 is in area 0. 104.1 is in area 104. And then we have area 24 that connects over to router 2 and area 34 that connects over to router 3. So the first thing that I want to do is I'm just going to check my database on router 4 to make sure that I see what I expect to see. Show IP OSPF database. And we're not going to investigate this from the perspective of, all the different concepts of OSPF routing that we talked about in our OSPF section. I'll have to go back and take a look at those if you need a refresher on that. But we can see area 0, sure enough, we have 2 links in area 0. That's interesting. Show IP OSPF database. I have a feeling it's because it's identifying that as a loopback. Show IP OSPF database router. And we're seeing, the 1.100. That's what I would expect to see. And it looks like 1.0 is also in area 0. Is that correct? 1.0. Yeah, I don't have it on the diagram here. Sorry about that. I actually have another Ethernet link, Ethernet 1.1, that's configured on router 4. It's also in area 0. All right. If I do a quick show IP interface brief, you can see that. Ethernet 1.1, even though it's not on the diagram, it's participating in area 0. So again, a show IP OSPF database. All I'm doing basically here is I'm just trying to verify that I'm getting everything that I expect to get, right? I should see type 3 LSAs for the prefixes that don't exist in area 0. This is area 24, this is area 34, this is area 104. So it does look like I'm converged. I should also have 2 neighbors, show IP OSPF neighbor, and I do have 2 neighbors, router 2 and router 3. So everything looks good. I could do a show IP route OSPF. I'm not getting any, makes sense, because if you look at the topology here, these are connected networks, but I do know that they're running OSPF. Remember, you can also do a show IP OSPF interface, because show IP OSPF interface will indicate the connected interfaces that are running the process. So if I do a show IP OSPF interface brief, I can see that all my interfaces are running OSPF. Loopback 100, Ethernet 1.1, serial 2.0, Ethernet 1.0, loopback 104. All right, these are basically the checks that I would go through on the lab as well, right? Because ultimately, you may jump right into configuring redistribution and it doesn't work, and you're troubleshooting the redistribution process, but the problem doesn't have anything to do with redistribution because an interface is shut down or misconfigured or something like that. And that's a consideration that you have to check. because don't spin your wheels trying to figure out what's happening with redistribution until you verify that everything else is working. All right. Now I'll do the same thing on router 1. Router 1 should have an EIGRP neighbor, show IP EIGRP neighbor, and it should also have some routes, show IP route EIGRP, because not all the networks are directly connected in this particular case. So you can see the loopback on router 2 is learned. The link between router 2 and 3 is learned here. The loopback on router 3 is learned, and so on. All right. So I'm just going to check one more thing on router 2. Show IP OSPF neighbor. I should have one neighbor. Yep, router 4. And show IP EIGRP neighbor. I should have two neighbors. This is the link between 1 and 2. This is the link between 2 and 3. This is router 3's address. This is router 1's address, and so on. So it looks like we're good to go with regard to show IP EIGRP neighbor, show IP OSPF neighbor. All right, so it looks like we're pretty much good to go on convergence from that perspective. All right, that is definitely something that you want to get into the habit of doing, is doing your basic checks before you start to do any kind of advanced configuration. All right, now let's configure redistribution on the routers. And while I'm doing this, I'm going to go ahead and talk about some of the different settings. Let's start first by going from OSPF into EIGRP. All right. And based on the diagram here, we have two redistribution points. We're redistributing on router 2 and we're redistributing on router 3. All right, let's start with router 2. Yes, somebody have a question? All right, so we're going to go into the EIGRP process because we're going to take routes from OSPF into EIGRP, and we're simply going to do a redistribute OSPF. Let me do this first. Do show IP protocols. We're running OSPF process number 1. So redistribute OSPF 1. Now you'll notice here I have an option. I can hit carriage return. Okay. And if I did that, and I went up to router 1, and I do a show IP route pipe include DEX, you'll notice I don't have any routes, right? Now the reason I don't have any routes is because of how the routes are being redistributed on router 2. If I come in here and I do a show IP EIGRP topology, no tab completion there, I can see that I don't have any routes coming in from OSPF. And again, this is simply because I did not specify a seed metric for the redistribution process. So EIGRP can't install these routes into the routing information base, which means they can't be, or the routing database, I should say, which means they can't go into the RIB or the FIB on the router. Okay. Now I could have done redistribute OSPF 1, and then I could have said, okay, let's go ahead and set the metric for the redistribution process, and I'll have bandwidth, delay, reliability, and load and MTU that I would specify as part of that process. Or I could specify a default metric which would then apply to all redistribution processes under the EIGRP autonomous system. Okay, meaning that if I redistributed RIP, I've redistributed connected, redistributed anything else into EIGRP, this default metric would basically apply to that. So a lot of people like to kind of do this because they have some consistency on you know, how the routes are going into EIGRP. Now, if I want to be able to manipulate that process, I want to be able to manipulate, you know, say RIP differently than OSPF and so on, then I would probably want to apply metrics directly to the process, to the redistribution process. So one of the things that I need to do is I need to figure out, okay, what seed metric do I want to apply? Now, if I'm looking at this topology here, let's say that router 1 wants to route over to the loopback on router 4, 1.100. The best path, most likely, even though it's not the shortest path by hop, the best path most likely is going to be down from router 2 to router 3 and then over to router 4. That's ultimately going to be the best path based on bandwidth, delay, other components. But I have to determine what seed metric I apply when the traffic comes into this network. Let's say I decided that I wanted the path through the serial link to be chosen. I might inject a different seed metric on router 3, which is much higher than the seed metric that might go in on router 2. In this particular case, though, I'm going to, I don't want to necessarily pick arbitrary values. So I'm going to pick, based on the ingress interface from OSPF, what those metrics are going to be. So I'll do a quick show, show interface serial 20 pipe include BW. All right. And I'm going to use these values based on just the fact that this is a serial link. So I'm going to do a default metric, and I'm going to specify the bandwidth in kilobits per second. So that'll be 1544. I'm going to specify the delay in tens of microseconds. The delay in show interface output is done in microseconds. So I'm going to do a 2000 instead of a 20,000 because I'm dividing by 10 because it's in tens of microseconds. Now, reliability, load, and MTU don't really matter in this case. These are not components of the EIGRP metric by default. So I'm going to just make this 100% reliable. I'm going to set the effective loading to 1, which is the minimum loading, and then I'm going to set the MTU to 1500. This actually should not affect the redistribution process because, again, EIGRP is not really considering these values when it's making its path selection. All right. Now if I go to router 1 and I look for those DEX routes, we can see that the routes are coming in from OSPF with a metric of 2195456. They all have essentially the same metric. That's cumulative metric based on not the delay, not the bandwidths, because the lowest bandwidth is what we specified on the redistribution point, but cumulative delays, right? We're still adding the delay between router 1 and router 2. So the 1.0, the 1.100, 24.0, and so on, they're all coming in to the routing information, a routing database, EIGRP routing topology database, and they're getting calculated as valid routes to go into the routing information base. All right. Now, let's go ahead and do the same thing on router 3. All right. Show run pipe section EIGRP. And in this particular case, we are redistributing on router 3. Oops, clicked the wrong link again. We're redistributing on router 3, so I'm going to take a look at Ethernet 1.0 as kind of my reference point for the seed metric that I'm going to send into into the redistribution process in this case. So router EIGRP 100, redistribute OSPF 1. And we're going to do the metric on this case as not a default metric, but we'll specify the metric in the redistribution process. All right, so the bandwidth, let's do this. Do show interface Ethernet 1.0 pipe include BW. And let's do a metric of 10,000, a delay of 100, reliability of 255, load of 1, and MTU of 1500. Okay? So if I go back to router 1, does the route change? And in reality, it doesn't. All right. Now, did the metrics change? Metrics didn't change either. Okay. Now, if I wanted to verify whether or not redistribution was actually occurring, I certainly would just have to go into the router that's doing the redistribution, do a show IP EIGRP topology, and I should be able to see those routes in the topology database via redistributed is going to be what the next hop is. So the 104 is coming in, the 1.0/26 is coming in, and so on. All right, so we can definitely tell that redistribution is taking place. There's a slight issue here. We'll get to that in a little bit when we do our redistribution in the other direction. If I look at my topology diagram, I'd like R1 to be able to go over to 1.100, but I would like it to take the path through R3. Now, that's not going to happen regardless in this case, because we haven't redistributed the EIGRP routes back into the OSPF domain. All right. So there would have to be some way for router 4 to reach, either through default routing or some other method, router 4 to reach router 1. We haven't done that quite yet. All right. We are definitely getting the prefixes though. But what happens if both those routers have the same router ID? If I come in here and I do a show IP protocols, include ID, there we go. So the router ID for this particular router, yeah, that didn't work. Well, yeah. So this is, we're looking at OSPF and EIGRP. In the case of EIGRP, this became the router ID. Let's just do a show IP protocols, and we'll do a section EIGRP. So we can see that the router ID, let's just do this. The router ID for EIGRP 100 is 172.16.102.1. Okay, so that was the router ID that was chosen. Router IDs are going to be selected essentially the same way as they are in OSPF, unless they're specifically or statically configured. In the case of OSPF, that is the case because the router ID is 2.2.2.2. The router ID is going to be the highest loopback that's active, highest physical interface, or we're going to trump over all of that by doing static configuration. So the router ID in this case is 172.16.102.1. Now, if I were to go into router 3 and go into EIGRP 100, and I were to specify the EIGRP router ID as the same router ID, and let's see how that affects. Let's do a clear IP route star, and we'll do the same thing on router 2. Do a clear IP route star. All right. Now notice we're still able to form an adjacency between the routers. Okay. Router ID is not something that is looked at between EIGRP endpoints with regard to forming an adjacency. In OSPF, this would not be allowed. OSPF routers would complain. They would not be able to establish an adjacency as they have the same router ID. Question is, do I have the routes in my routing table? Now I shouldn't, but I do. Why is that? Show IP route 172.16.1.0, and let's see, update 12.2. Wonder why that is the case. Show IP protocols. 172.16.102.1. Let's make sure it took hold here. Show IP protocols here. And for EIGRP, it's interesting. Let's see. I don't see router ID listed. Oh yeah, it is 172.16.102.1. So there's definitely a conflict here. What should be happening in this case is that the routes should not be installed. I guess they would go into router 1, but they would not go into each other. I may not be able to actually demonstrate this in this case because we're basically redistributing the same networks on both endpoints. Router 2 is not redistributing a route, and then router 3 redistributing that same route to router 2. So the fact that they have the same router ID in this case doesn't really affect us. But in any event, if that were the case, if router 2 is redistributing a route and then router 3 happened to be redistributing that same route back out, router 2 would ignore that route because it has the same router ID as part of the process. So I can't demonstrate this. Show IP route, EIGRP, D routes. I'm going to leave the router ID for now. That's the same because the D routes are obviously there. The DEX routes are not there for those OSPF networks for a reason. We'll talk about that in a minute because that's going to be another issue that we're going to have with EIGRP. All right. So as far as redistribution goes, basic concept here, show run, pipe, section, EIGRP. We go into the process that we want to do the redistribution in. So we're going to bring routes into EIGRP. We use either the default metric to specify a seed metric, and then we use a redistribute command. Now later on we'll talk about how do we apply a route map to this, how do we manipulate variables of the routing process in the redistribution process. We'll get into a lot more of the advanced functionality a little bit later on. But remember, going into distance vector, whether it's RIP or EIGRP, you have to specify a seed metric. Okay? All right. Now, I'm going to leave the router IDs the same for now. I don't think it's actually going to break anything because we're not doing redistribution in both directions for the same protocol. But we're going to go ahead and leave that there. All right. Now, as far as OSPF goes, OSPF uses the same administrative distance for all the routes. So whether it's redistributed, internal, external, OIA, OE1, OE2, ON1, ON2, they're all going to have an administrative distance of 110. We use the router ID in OSPF much more effectively, actually, for loop prevention as well. All right, there's actually a state in the OSPF state machine that says if the originator of the route is me, then I'm not going to install that route because it's being reflected back to me. All right, EIGRP does this kind of natively in the opposite direction with split horizon and also with the router ID option that's sent in the internal and external routes. All right. Now, unlike EIGRP, where there's no default seed metric in OSPF, the default seed metric is 20, and that's a cost. That's a cost value. So we're inserting a default cost of 20, and the routes are either going to come in as OE2 or ON2. All right, meaning that the seed metric doesn't change as I move through the autonomous system. So if the routes are being sent in with a cost of 20, they're going to remain a cost of 20 regardless of wherever we go. That's the default behavior. You really have to take care if you have two-way mutual redistribution. All right, in our topology, we're actually going to see this issue. We know that OSPF has a very detailed selection process when it comes to choosing routes. For example, E1 routes are going to be selected over N1 routes, and E2 routes are going to be selected over N2 routes, and so on. But that doesn't always apply, right? E1 and N1 versus E2 and N2, the choice between those is going to be based on forward metric, and that's going to be the key. So even if I might have two E2 routes with the same metric of 20, we wouldn't load balance unless they had the same forward metric. And that's not through the redistribution process because there's technically no forward metric in the redistribution process, but I'm talking about in general the route selection process. So now let's redistribute EIGRP into OSPF and talk about some of those considerations as well. All right. So now I'm going to go into router OSPF. Router OSPF 1. And I'm going to say redistribute EIGRP 100. All right. Now I'm just going to use the default behavior here. We saw that we just got a warning. Only classful networks are going to be redistributed. Let's talk about that. All right. So this is another one of those kind of golden rules when it comes to redistribution. Whenever you're redistributing out of EIGRP, all right, whenever you're redistributing out of EIGRP, or let me rephrase that. Whenever you're redistributing out of distance vector, so this would apply to RIP as well, only classful networks are going to be redistributed by default. So if I go to router 4 and I do a show IP route, you'll notice I don't have any EIGRP routes, even though I am doing redistribution. It's not because of the seed metric, it's because these are 172.16 subnets, but they're not classful. They don't have /24 masks applied to them. So this is a really, really important concept. When you're doing redistribution from distance vector, you have to use the subnets keyword to indicate that you want to redistribute all of the routes, not just the classful networks. So if I go back to router 2 and I add the keyword subnets at the end, now if I go to router 4, I should see my OE2 routes. You'll notice that they're coming in with an administrative distance of 110, which looks like a normal OSPF route. They have a seed metric of 20, and they're coming in as OE2. All right? That's going to be a problem in our topology. I'm going to demonstrate why that's a problem in a second here. That's going to be a problem in our topology because we want to influence the path that's going to be selected for these particular routes. Let's go ahead and do the redistribution on router 3 as well. Config T, router OSPF1, redistribute EIGRP 100 subnets. So now we should have full convergence. I should be able to go over to router 1 and ping the 1.100 loopback on router 4. Which I can. If I do a show IP route EIGRP, I can see the 1.100 route listed there at the very top. But am I taking the best path? Am I choosing the best path to reach that particular destination? Conversely, router 4 should be able to ping the loopback on router 1. Ping 172.16.101.1, which I can, no problem. Now if I do a show IP route 172.16.101.0, you will notice here that I am learning about that routing entry, and it's known via OSPF1. The metric is 20. It's coming in as type 2. The forward metric is 10. So we can see that we're actually going to router 3 to reach this particular destination. This is where there's a big distinction between how OSPF handles routing and EIGRP, right? Even though technically speaking, this route is being inserted. For example, if I come into, if I look at the topology here, the path that's being chosen to get to that destination is this link here between R4 and R3. Now, if I shut down Ethernet 1.0 on router 4, all right, and I do a show IP route OSPF. Let's do a show IP route 172.16.101.0. You can see that I still have a destination. I'm now going to router 2 for that destination, but the forward metric is 64. This is the cost for me to get to the ABR. Again, this goes all the way back to our OSPF discussions where we were talking about the difference between the metric for the route versus how OSPF reaches the advertising router, which in this case is the ABR. All right, so think about that for a second. It's actually good behavior, right? We want OSPF to take that faster link to reach that particular destination. Let me go ahead and turn that interface back on. And let's go ahead and look at our route again. We should be going back to router 3 once we've converged. Show IP interface brief. Make sure I turn on the right interface. Yep. So I should be going back to router 3. There we go. So now I'm going back to router 3 for that particular destination. Again, based on the forward metric. You saw the convergence took, here's a forward metric of 64. This is when we switched over to the new path. That was probably because of the adjacency process taking place between the two peers. Okay. So router 4 is going to choose the Ethernet path to reach router 1. But if I go to router 1 and I look at this destination, if I do a trace route to 172.16.1.100, all right, you'll see that it's going to router 2 and then it's going directly to router 4. So this is a situation where you've done redistribution, very basic concept, very basic configuration. You've done redistribution, but guess what? It's not working the way you expected it to because we now have asymmetric routing. The traffic is going in one direction, going over the serial link from the EIGRP domain to the OSPF domain, and then it's going over the Ethernet link on the return path. Why is that? You guys have any idea why that's happening? Any thoughts at all? Well, that's why you're here. So I'm going to show you why that's happening. Has nothing to do with the metric, actually. It has to do with routing decisions. More specifically, it has to do with administrative distance and how the routers are choosing a path based on the lowest administrative distance. Think about it. What is the administrative distance for OSPF? It's 110. What is the administrative distance for EIGRP? 90. But what is the administrative distance for redistributed EIGRP? It's 170. Okay? So that means that when the traffic goes from router 1 to router 2 needs to make a decision. Am I going to route down to router 3 based on the route that was redistributed from OSPF? Or if I'm going to route natively using OSPF, I'm going to route natively using OSPF. I'm going to take this path here because I'm learning about 1.100 through OSPF with an AD of 110, even though this is a better path this way because it has an administrative distance of 170. All right? These are the kinds of things that you need to consider when you're doing redistribution. You have asymmetric routing here. Who knows? They might introduce this kind of concept on the exam, and you have to figure out why packets are not reaching their destination. Or they may even ask you to manipulate how the routing is taking place by sending it in a particular, through a particular path or through a particular destination. So we actually have to manipulate on the router's administrative distance. Now we will look at this in more detail as we go through some of the other examples a little bit later on. But I'm actually going to go into the EIGRP routing process, and I'm going to say distance for EIGRP, and I'm going to specify the distance for my internal routes. So I'm going to go ahead and leave that at 90. And then I'm going to specify my distance for external routes, and I'm going to make that 109, right? Let's just make it 100. Anything less than 110 is going to be great, right? I'll do the same thing on router 3. I want consistent routing. Router EIGRP 100, distance EIGRP. By the way, the other option, distance and then a number, that's where I would apply it to a specific peer. So if I want to change the administrative distance of routes that I'm learning from a particular neighbor. In this case, I'm applying this to the entire EIGRP process. So I'm going to apply it to EIGRP. So now if I go to router 1 and I do my trace route, you can see I should end up choosing the path through router 3. Okay. Now this may be the case now where the router ID is causing a problem because I should definitely be going from router 2 to router 3. I believe router 2 is ignoring those routes from router 3 because of the router ID. So let's go ahead and fix that. Router EIGRP 100, no EIGRP router ID. And let's do a clear IP route star. All right. Let's see if that helps us here. We should be going through router 3. Show IP route. So our DEX routes have an administrative distance of 100. That's good. But I'm not seeing, what am I tracing to? 1.100. For some reason, I'm not seeing the 1.100 route here. It's still coming in as OSPF. So this is good. This means something is not working. It's probably a GNS3 thing or a convergence thing. I probably have to shut some interfaces and reconverge here. But let's go ahead and troubleshoot it a little bit. I know why we're taking the path to router 2 from router 1's perspective, because router 2 only has one route installed for the 1.100 subnet, and it's through OSPF. So naturally, I'm going to go over that serial link to reach that destination. So my first step would be to do a show IP EIGRP topology and see if I see that prefix in the topology database and who's originating that prefix from EIGRP's perspective. So 1.100 is here as redistributed. I'll do the same thing on router 3, show IP EIGRP topology. And 1.100 here. Interesting. 1.100 is being learned by router 2 here. So it doesn't look like it's coming in via redistribution. In fact, I only see 34 via redistribution, and that's it. So I'm actually not even seeing 23 via redistribution. 104 is being learned from router 2. 102 is being learned from router, well, that's in part of EIGRP. 1.0 is being learned from router 2. 23 is being learned, is directly connected. So that makes sense there. So this is strange. What's going on here? Let's do a show run pipe section EIGRP. We haven't applied any filters to the redistribution process. Redistributing EIGRP using subnets. We could change those to E1 routes, but changing them to E1 routes is probably not going to make any difference. That's only going to affect how OSPF interprets those routes. So let's see. Let's do something here real quick. Let's just go into router 3. And I wish we were running EIGRP for IPv6. We could just shut down the EIGRP process. I'm just going to flap this link here, E11, and see what that does here, because this definitely is not the right behavior. Interface Ethernet 1.1. Let's clear our adjacency. All right, and we'll do a no shut. Bring up our adjacency here. Show IP route. Now let's do show IP EIGRP topology. And 34 redistributed. Still 1.100 is coming through router 2. And I'm trying to figure out why that is the case. Both of them should have the routes installed in the topology database based on the fact that they're being redistributed. And that is affecting our path selection. I've done this exercise many times, and this is not the way it's supposed to work. Let's do this. Let's go into interface serial 20. Shut that die down. And let's make sure that we're actually getting to that destination through router 3. Okay, so we definitely have reachability through router 3. And that is proven here because we shut down serial 20. We know that we have reachability. So we know the redistribution process on router 3 is working just fine. Just not sure why it's not kicking over as it should. Our seed metrics should influence the process unless I put in the wrong seed metrics. So it looks like now we are taking the correct path. I just flapped that serial link. And let's see here. Show IP route 172.16.1.100. So that's going, it's learned through EIGRP from router 3. And that's the way it should be behaving, right? Because the administrative distance is 100. That's going to be preferred over OSPF. Even though router 2 is learning about the route through OSPF, it should not be choosing the route through OSPF because it should be choosing the route through router 3. Could be an order of operations things that we're running into here as well. But in my experience, I've done this particular topology many times in this discussion. This has not been the case. So I'm not sure specifically why it didn't do that, what it was supposed to do. But now it's responding the way it should be responding. Just to see if it's a convergence issue, I'm going to shut down Ethernet 1.0 on router 3. We should go through router 2. for that destination. And what should happen, we didn't converge yet, so should be converged pretty soon here. We've got some hold time. Let's do clear IP route star. So router 2 thinks it can get, so it's going directly to router 4. It's just a convergence issue here. We should end up going to router 4. Okay, so it is going to router 4. I'm not sure why we're getting that timeout. We're in the process of kind of reconverging and routes being in hold down states and stuff like that. But so now if I bring up that Ethernet interface, what should happen is we should end up going through router 3 eventually. As router 3 comes up and starts redistributing routes, router 2 should say, wait, I'm hearing about this route from router 3 with a different router ID, so I should be able to install that route. And it may be I broke it because I was messing around with the router ID. It should be cleared out though. So it doesn't look like GNS3 is responding the way I expect it to. I'll explain what's happening here from a testing perspective. What's happening here in this case. What should be happening is natural behavior and what's not happening. All right, so just to kind of re-clarify what we were talking about, going from OSPF to EIGRP, if I'm redistributing routes from OSPF into EIGRP, get this guy into snipping so I can draw on it. Come on. All right, so if I'm redistributing routes from OSPF into EIGRP, they're going to come in with an AD of 170. All right, now router 2 is participating in OSPF, so it's learning about the same prefix with a 110. So naturally, the 110 is going to be selected over the 170 because 110 has a lower administrative distance and it's the exact same prefix. All right, so what we did is we changed the behavior of EIGRP to say that the administrative distance for redistributed routes is now going to be 100, right? So as these routes come in, they go from 110 to 100. Same thing here, we go from 110 to 100, which means that the EIGRP, the external EIGRP routes are going to be preferred over the OSPF route. Now, because we're sending this route in with a higher seed metric than this route, what should happen is router 1 should take this path based on that higher seed or lower seed metric. Because router 1 is technically going to be learning about the prefix from 2 routers, but it's going to choose the best path, which in this case should be router 3. In fact, actually the metric doesn't even really come into play from router 2's perspective, because router 2 knows how to reach 1.100 through OSPF. Router 2 knows how to reach 1.100 through EIGRP. It should choose the EIGRP path through router 3 automatically because of administrative distance. So something's going on here with the convergence. I'm not sure what's going on. Normal behavior would be that as long as R3 is advertising that same prefix with a lower administrative distance, then router 3 should be the chosen path. We already know that OSPF, based on our investigation of path metric, right? Not just seed metric, but path metric, that OSPF is choosing to go through router 3 because the cost to get to that ABR is 64 and the cost to get to that ABR is 10. So we're going to choose to go to that ABR for the same destination prefix, which means we should have asymmetric or symmetric routing. All right. We'll take a look at some other options in this redistribution process. I want to wrap up today's lesson by talking a little bit about BGP. We're not going to look at BGP redistribution just yet. We're just going to talk a little bit about some of the caveats And then we'll wrap up this lesson. In the next lesson, we'll take a look at some of the some of the considerations with regard to loops in redistribution. All right. Now, BGP has a special packet type. It's called an origin code. And any routes that are redistributed into BGP use an origin code of incomplete, which is referenced as a question mark. Okay. Incomplete routes are always less preferred than one that has, say, an internal code. Let me see if I can show you what I'm talking about here. So if I go to Google here and I do a search for BGP path selection process, if we look at the BGP state machine and take a look at the path selection algorithm, we start by looking at things like AS path, weight, and so on, right? So the first thing that we see here that's listed is path with the highest weight, prefer the path with the highest local preference, prefer the path that's locally originated via network statement, prefer a path with the shortest AS path, and so on. Prefer the path with the lowest origin type. All right. This is the one that I'm talking about right here. So selection number 5, prefer the path with the lowest origin type. IGP is going to be lower than EGP, IGP meaning OSPF, ISIS, etc. EGP is going to be lower than incomplete, incomplete meaning redistributed routes. So if you go into a BGP table, all right, and show IP BGP, incomplete, you will see in the BGP routing table, you'll see these entries that have a question mark with them next to them. That's the origin code. So I does not mean incomplete. I means IGP, or internal, excuse me, and question mark means incomplete. Simply means that the route was not originated using a network statement. All right, so we go through our whole selection process. Like I said, selection number 5 is what the origin code is. All right, loop prevention in BGP is taken care of automatically with eBGP using the AS path attribute. iBGP uses normal advertising rules, right? Normal advertising rule for iBGP is that iBGP peers cannot advertise routes to a downstream IBGP neighbor, if they learned about that route from an upstream iBGP peer, right? Which means we cannot re-advertise routes that we learned from other iBGP peers. The exception to that would be if you're running a route reflector, or if you're doing some sort of confederation eBGP neighbor relationship. That's going to change that behavior. We'll get into a lot of that stuff later on when we go into our BGP discussion. All right. Other considerations when it comes to BGP, typically we're going to run BGP between a PE and a CE router. In that case, we don't need to do redistribution to go from eBGP to VPN-v4 BGP. And we'll talk more about that when we get into our MPLS section. All right. The other thing to think about, though, with BGP is we need to consider the direction that we're redistributing. If we're going from IGPs into BGP, or if we're going from a BGP into an IGP. All right? Now, if I'm going from an IGP protocol into BGP, and I'll show you guys this a little bit later on, but if I'm going from an IGP protocol, like OSPF, into BGP, BGP is going to deny OSPF external routes by default. And the reason being is that BGP is going to say, well, if it's OSPF external, that means it's coming from outside the domain anyway, and it's not a route that's originated within the domain. Okay? There may be cases where you want that to take place, right? So if I do a redistribution, let's say I do redistribution of OSPF into BGP, I would go into the BGP routing process, I would type redistribute OSPF 1 or whatever, and then I would use the command match internal external. This will change that behavior, and it will allow those OSPF external routes to be routed into BGP or sent into BGP. That's something that we'll take a look at later when we actually do our configurations. If I'm going from BGP to an IGP protocol, we have to be very, very careful, because typically in this particular case, you're talking about tens of thousands, hundreds of thousands, or even millions of routes that could overwhelm the IGP routing process. Now, eBGP routes do allow routes to be redistributed, but IBGP routes are going to be denied by default because we're going to trust the internal routes over IBGP routes. If it's internal, I should be trusting my IGP routing process as opposed to some sort of IBGP routing process. So to prevent very large databases from going into your IGP, make sure that you do some sort of route filtering, use some sort of IGP protection, and you know, from a real design perspective, that's typically done. Okay. Now, if you do want internal BGP routes to be redistributed into your IGP, you would use the BGP redistribution -internal command, and that's going to turn off that behavior. All right. Like I said, we'll get into that a little bit later on. I don't want to put too much on you guys right now in this lesson here, and I think that's enough for our initial discussion. We looked at some of the basic examples. We talked about some of the caveats and some of the considerations. We will get into some more advanced configurations and actually some break-fix scenarios when we get into some of our later redistribution discussions. All right? So unless there's any questions, we'll go ahead and wrap up this lesson, and then we'll see you guys in the next lesson.